If I were to ask you, what's the volume of this sphere? What would you do? Well, the first thing most people would do is they would just look up the formula for the volume of a sphere, right? The volume of a sphere equals 4/3 times pi times whatever the radius is cubed. So if you wanted to find the volume of this sphere, you would plug in 3 centimeters for the radius, cube it, multiply it by 4/3 pi, and bam, you would have your volume. Well, maybe you're wondering, where did they even get this formula? Right? Because we always look it up and we see that this is the formula for a sphere, right? Or, we can find the volume of a cylinder or the volume of whatever shape we want. But how did we actually get these formulas? Or maybe I'm asking you, if this radius isn't constant, let's say the radius is increasing at a rate of 2 centimeters per second, at which rate is the volume increasing? How could we figure that out? Well, if we're trying to find the rate at which something's increasing, this formula means nothing to us because it's assuming that everything is staying constant. It's assuming that the radius isn't changing and therefore the volume isn't changing. But what if things are changing, right? Or maybe I want you to find, the vertex of this equation, y equals x squared minus 2x plus 2. Okay, what if I was trying to find the vertex of this? If I were to graph this function, what would the vertex be? Well, typically people would complete the square, or they'd use the formula x equals negative b over 2a. That's your x coordinate of the vertex. Once you have your x, you can plug that in for the x value to figure out what the y coordinate is of the vertex, blah, 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 all this long, kind of this whole process. But with calculus, we can figure out the vertex of this thing like instantly without doing all the extra work. Okay, so the main branches of calculus, if this is kind of your calculus tree here, there are two main branches. Okay, so the first branch of calculus is called differential calculus. Okay, the second branch is integral calculus. So differential calculus deals with something called derivatives. Derivatives are all about finding the rates at which something changes. Okay, so to find the rate at which the volume here is changing, or if we have the rate of the volume changing, we can find the rate of the radius changing. That's all dealing with rates. Okay, or maybe we wanted to find the slope. Let's say we had this function here. Maybe we wanted to find the slope of this curve at x equals 7. Okay, so when our x value is 7, what's the slope of this curve? Right? What's the slope of the tangent line? The line that just touches the one point at x equals 7. That's kind of the main idea with differentiation. Okay, with integral calculus, we're more dealing with the opposite of derivatives. Okay, so just like the opposite of adding is subtracting. So if we had y equals, or let's say we had 3 equals x plus 2, right? To figure out what x is, we would subtract 2 because subtracting is the inverse operation to adding. So we'd find that 1 is equal to x. Integrals are the exact same thing. So integrals are the inverse operation to derivatives. Okay, so if we had the equation y equals x squared plus 2, if we differentiated this, and the notation you would do for that is y prime, so this is the derivative of y. You could use something called the power rule, which I'll explain in the next video, and you'll find the derivative of x squared plus 2 is going to be 2x. Okay? If you wanted to go the other way, you would find the integral. Okay, you would find the integral of the derivative. If you found the integral of the derivative, you would just get y back because integrals and derivatives are inverse operations. So the form you take for this is you'd say the integral of 2x, and then you put this little dx here, okay, just to show us with respect to x. You're going to use another rule with integration that I'm going to teach you later. This is going to be 1/2 times 2 times x squared. Okay, 1/2 times 2, that's going to be 1. So we're just left with x squared. And we always have to add this plus c here. You'll figure out why later. But notice how we end with x squared after we integrate the derivative. And right here, we started with x squared as well. And this plus c kind of attached to the end, that's going to account for our plus 2. Okay, so anytime we integrate a derivative, we're just going in the other direction to give us our original function, which we started with. Okay, so calculus, it's split up into differential and integral calculus. Later on into calculus, there's going to be different types of derivatives. So there's going to be something called partial derivatives, which look like this. They kind of have these funky D's, these curly D's, which stand for, they basically mean that we're dealing with multiple variables and we have to kind of split it into two parts. Okay, so let's say we had the equation z equals, or no, I'll say, if we had kind of a function that was composed of two variables, x and y, if it was 3y squared minus 2x, if we wanted to find the derivative with respect to x of this function, we would have to use partial derivatives. So we would have to use this curly bracket, derivative with respect to x of f of xy. So when we're doing this, we treat everything that's not an x as a constant, so the y, the 3, and the 2. But if we wanted to find the derivative, the partial derivative with respect to y of f of xy, we would have to treat the x's and the numbers as constants. Okay, so I'm not going to go too in depth onto how to solve differential and integral equations or expressions, but that's the basic idea. So calculus allows us to find rates at which things are changing. Also, what integrals actually do is just kind of the opposite to derivatives finding the slopes of curves. So let's say we had a similar curve. Integrals allow us to find the area under a curve. So let's say this was x equals 2, and let's use that point we had before, x equals 7. If we were to integrate this function, so let's say we called this f of x. Okay, our function is f of x. If we were to integrate f of x with respect to x from the x values 2 to 7, here we have to add this dx here, that'll give us our area under the curve from x equals 2 to 7. Okay, so if we were to integrate this with our bounds being 2 to 7, it would give us this area here, which can be super helpful in lots of different equations. Like say, if we had just a linear function, right? If we had a linear function that looked like this, we wanted to find the area, let's say from 0 to, let's say this was 5. This was 5. How would you do that without calculus? Well, you'd split it into two shapes. You'd split it into a triangle. We know the formula for triangles. We could split it into a rectangle. So you'd find the area of this rectangle, the area of this triangle, and you would add them together. Okay, but with calculus, we only need to differentiate the function, to integrate the function. Once we integrate the function, then we have our area all at once. We don't have to split it up into two different problems. Okay, so calculus saves us a ton of time from doing lengthy algebra and all this stuff. It's a really efficient way of figuring out some really cool things, and I'll teach you what those things are in future videos. So just stay tuned and we'll learn more about some calculus.